Welcome. Hi, it's Dr. Bonner here, and this is a good video. Now, picking my favorite video is kind of like picking my favorite child. It's really easy. This is definitely my favorite. This is the most important, really, law for physics, right? I mean, Newton's laws doesn't get more fundamental than that. And we're going to do a lot more with writing the force equations moving forward after this video and getting into solving problems with this. So let's get to it. First off, we have to understand, why do we even care about Newton's laws? What are they, but really why do we care? What can we do with them? We're not going to do grade school memorization of some statement, like an object in motion stays in motion, that kind of thing. We need to be able to apply it. So the essence of Newton's laws are that they match up the state of the forces being balanced or unbalanced with the state of the motion having an acceleration or not, right? So we have two different instances. In one case, you can have balanced forces, which coincides with no acceleration. It could be moving, right? You can have a velocity, but that velocity needs to maintain a constant value because there's no acceleration. So on the other hand, if you don't have balanced forces, you can have unbalanced forces, and that means that the motion has to be accelerated. We actually know this as an equation. So net force equals ma is Newton's second law mathematically. And you notice here it says section 2.5, and that's because after this Newton's laws video, we're going to start using Newton's second law to write force expressions as we solve problems. So we're going to work backwards here a little bit then. So Newton's law is where we're going to end up. So again, working backwards, we can say then that section 2.4 is Newton's first law, and that would be summarized as the balanced forces and no acceleration, which is aligned with that statement of an object will maintain whatever motion it is unless acted upon by an external force. So if we apply Newton's second law, which should hold true, all this is saying is if you have no net force, you have no acceleration. So again, working backwards, 2.3 is Newton's third law. So we're going to start with Newton's third law, and then we're going to work our way to the F net equals ma and Newton's second law. So Newton's third law. The summary for this, the gist of it, is that forces are going to exist in pairs. Every force exists in pairs. And so there's a force between two objects, and they have to be equal and opposite. So another way to think of this is it takes two to tango. There has to be, for every force that acts on object A by object B, there has to be then the flip side of that, which would be then the force on B by A. I can't touch something without it touching me back. You can try all you like. I promise you can't do it. So let's take a look at a familiar example here where we have Jim pushing a car. So Jim pushes on the car, right? So there's a force on the car by Jim. So what Newton's third law would say, if we switch, then there would be an opposite but equal force on Jim by the car. And so these have to be the same magnitude or same strength, just in opposite directions, according to Newton's third law. This is very helpful in complicated problems where we have multiple objects because it creates a shared variable as the force between them. So let's take a look now at Newton's first law. And we'll look at some examples of some situations here. So I'm going to lift this backpack up at a constant speed. So the question would be, how does my lifting force compare to the backpack's weight? As in, is it a greater lift than the weight? Is it an equal lifting force with the weight? Or is the lift less than the weight? So if you think to yourself, what would you answer and why? So to answer this problem, we're going to look at a force diagram. And so the points of contact would be really just my hand. That's the only thing touching this backpack. So there would be an upward pull, which we could call tension from my hand on the backpack. And of course, we'd have gravity. So the no acceleration label that I often make ninth graders in honors physics do is really important because that's going to tell us if those two arrows are balanced or if one's bigger than the other. In this case, no acceleration, I know is going to then require balanced forces. So when I do a free body diagram where length is strength, I make force gravity 2 boxes, then I can either show tension as being bigger by making tension 3 boxes, I can make tension equal by making 2 boxes, or I can make it less by making it one box. So by knowing that this is going to be two boxes because of Newton's first law, then I can answer this question either by a check mark here or through a free body diagram. If this isn't convincing to you, let's take a look at me lifting a backpack, but you can see here that I'm holding it up with a sensor here. Okay, so when we look at this now, I'm going to lift it up. I'm going to hit go, and you can see here that the force tension is 0 when it's balanced, and then as I move it away, this tension will either go above gravity or lower. So as I'm lifting it up, you can see here that it's still equal tension. Tension isn't bigger or smaller than gravity. Again, if we look at this, tension is balanced with gravity when I'm just holding it still. When I move it, you can see tension gets bigger or smaller, and as I move it up at a constant speed, the tension is still balanced with gravity. It doesn't matter that it's moving, it only matters if it's accelerating. Let's take a look at this one. This is my friend the leprechaun, so he's hanging by a string. And in this case, if we, again, look at tension being zeroed out when he's hanging there, you can see it moves a little bit. So as I pull him up with a constant speed, you can see it's going to hover right around 0, and then it'll move when I stop. And then as I lower him, again, it's going to hover right around 0. So again, if it's balanced forces, it doesn't matter if it's moving, it's just if it's accelerating. That's a key point. You may want to jot that down. It doesn't matter if it's moving to the forces. Unbalanced forces just care about acceleration. In fact, we don't even need to have balanced forces. We can have no forces, and that's technically balanced as well, right? Because then we can have this hovercraft that's just flying along. And if we look then a force diagram, you would have that surface pushing up and gravity pushing down. Now, are those balanced? Sure. Because there's no acceleration up or down. But then what would be causing it to move to the right? And that's simple, nothing. It doesn't need to have a force to move. It needs to have a force to accelerate, and it's not accelerating. So if we had a force to the right or left, that would create an unbalanced force and cause it to gain speed or lose speed. So in this case, once it's put into motion, it will stay in motion, which is a Newton's first law statement. Well, let's take a look at when something's accelerating. So Dr. Bonner, would you be able to help us out? Okay, can you just drop that ball? Thank you so much. So in this case, we have an acceleration, which should mean that we have unbalanced forces. Right, so then if we think about then the forces, the only thing acting on it is gravity when it's falling. So if gravity is equal to ma, then gravity being mg is also then equal to ma. Divide out the masses, and we're left at g, 9.8 or 10, is the same thing as the acceleration when an object's in free fall. Neat. Let's look at another example here. Now in this case, I have a washer, which is a mass that's hanging high over this pulley, and you can see there's a string, and that string is going to go all the way back, and it's going to be attached then to this yellowish color cart. You can see right there it's attached. You're doing a great job there. Okay, and what we're going to do is we're going to let go of this and allow the system to accelerate forward. You can see it's starting to gain speed. So let's take a look at what's happening here. So we have, for the cart, we have a tension that's pulling forward, normal force and gravity. And if we look at these x-axis, the tension is the only force, so we could set it equal to ma. For the y-axis, we would have balanced forces because there's no acceleration up or down. So how would this compare to then that mass that's hanging in the washer? So in that case, then we would have a tension and gravity. So gravity should be bigger than tension because it's accelerating downward in the direction of gravity. So when we write our expression, do we write it as Ft minus mg equals ma? Or do we write it as mg minus Ft equals ma? Or does it not matter? So that's a really common mistake I see students do. So we got to really unpack this one. What do you think it would be? Okay, well, let's see if you're right. Let's take a look back at our leprechaun one. Okay, so now if we hit collect again, it's going to be balanced when he's just sitting there. and then I let him accelerate up. You can see that the tension is bigger than gravity if he accelerates up. That makes sense, right? So if we look at a force diagram and I have this idea that they have to be different lengths because it's accelerating, and I know gravity is 2 boxes, I can make then tension 3 boxes if it's supposed to be bigger, 2 boxes is supposed to be equal, or 1 box is supposed to be less. And we know because tension's bigger, as you can see, it's larger than when they were balanced. It's larger, right, that tension. Then I can make that 3 boxes to show that it's larger. So which one of these would fit? Well, I should have a leftover amount, so I'm going to take the bigger force minus the smaller force. And if I do that, what I essentially can summarize that as a key point that we always want to do, just let the acceleration, if there is one, define what you call positive. So in this case, tension up, acceleration is up. So I would want then tension to be added, gravity is down, so I'll make it negative, so I subtract it, equal to ma. This would not work because we would end up with a negative acceleration over here. So this key point will really clear things up in these problems. What if you're accelerating down? How does that change things up? So again, we're going to hit collect when it's balanced, so you can see tension is pretty close to 0. And when it accelerates down, you can see the tension is less than gravity. So if we did our free body diagram with gravity being 2 boxes, then I'm going to draw tension as being less than gravity by only making it 1 box. And therefore, of these 2 options we have, let the acceleration define the positive direction. Down is the direction of the acceleration. So we're going to let mg be positive since down is positive. Acceleration is positive, which is down. So mg being down will also be positive, which would mean this would be the correct way to write it. So when students memorize this or just start to attach a pattern in their brain, it causes all kinds of problems. Best thing to do is that key, which is to let the acceleration define the positive direction. So this is a summary. I just took a picture of the board because I have this written on the side of the classroom. You'll probably see it if you look over there or over there if you're in the classroom. And you'll see that this has a lot of the ideas that we had built into it. Now, this is how you solve force problems. So this is like the next step. And you can see that we have points of contact from our drawing of force diagrams, or you could do a free body diagram, right? Then see, look, is it accelerating? Yes, then we're going to let the acceleration define positive. And that means you have unbalanced forces, right? And if it's not accelerating, then you have balanced forces. So this is going to play a key role in our problem solving as we get into eventually writing the force expressions that we need to do. And you can even see that Newton's third law plays into that when you have between any 2 objects, as it allows you to connect force equations from object A and object B since they have a force in common. All right, I hope that helps. Have a great day.